What if I told you that Earth has a shield, a vast invisible one that stretches over 100 times the distance from the Earth to the Sun? It's called the Heliosphere, and it does much more than just warm our planet. It protects us from cosmic dangers lurking in outer space. In this video, we will explore the enigmatic Heliosphere, delve into its formation, and uncover why it is crucial for protecting life on Earth. We'll also look at the challenges scientists face in studying its vast expanse and the future missions planned to learn more about the Sun's dynamic influence. The Heliosphere, an expansive shield generated by the Sun, stretches far beyond the planets to the edges of interstellar space. This shield is formed by the solar wind, a constant flow of charged particles that the Sun emits. This wind carries with it the Sun's magnetic field, extending its influence far beyond the visible planets and into the void of space, creating what we know as the Heliosphere. Drawing on the expertise of Sarah Spitzer, a research fellow in climate and space sciences and engineering at the University of Michigan, this exploration sheds light on the Sun's role beyond mere illumination. As described in her contributions to the conversation, Spitzer's insights help us understand the profound impacts of the Heliosphere. The solar wind is not a steady breeze but a tempestuous storm that varies with the Sun's activity. During periods of high solar activity, the Sun releases more intense solar flares and coronal mass ejections. These are massive bursts of solar material and electromagnetic radiation that, if directed toward Earth, can disrupt satellites, communications, and even power grids. The Heliosphere plays a critical role in modulating these solar emissions, acting as a first line of defense by deflecting and diluting these energetic particles. The structure of the Heliosphere is complex. At its core is the termination shock, where the solar wind slows down as it meets the interstellar medium, the collection of gases, dust, and cosmic rays that fills the space between stars. Beyond this shock lies the Heliosphere, a turbulent area where the solar wind begins to mix with the interstellar medium. The outer boundary of the Heliosphere, the heliopause, is where the Sun's influence ends, and the vast expanse of interstellar space begins. This vast bubble does more than shield the inner planets from galactic cosmic rays, it also preserves the conditions necessary for life on Earth by preventing these high-energy particles from stripping away our planet's atmosphere. This protective mechanism is pivotal in maintaining the stability of Earth's climate and protecting the biological processes that sustain life. However, the protective capacity of the Heliosphere isn't static, it fluctuates with the solar cycle, approximately every 11 years, influencing the intensity and reach of the solar wind. Understanding these cycles helps scientists predict periods of intense cosmic weather that could potentially pose risks to Earth's electronic infrastructure and astronauts in space. Given the Heliosphere's significance, it is a subject of intense study by heliosphysicists, who utilize both direct satellite observations within the solar system and computer simulations to predict and visualize the Heliosphere's interactions with the solar wind and interstellar medium. Despite its critical importance, much about the Heliosphere remains a mystery, primarily due to the immense challenges involved in directly observing this vast region. The shape of the Heliosphere is particularly contentious, with scientists proposing models ranging from spherical to comet-like or even resembling a croissant, each suggesting different interactions with the interstellar medium. The primary source of our current knowledge comes from the data returned by the Voyager spacecraft. Launched in 1977, Voyagers 1 and 2 have crossed the termination shock and the heliopause, entering the interstellar medium and sending back invaluable data about the conditions on the edge of our solar system. Their findings have reshaped our understanding of how the solar wind interacts with the galactic environment, revealing a more complex interaction between solar and cosmic forces than previously thought. However, the Voyager missions have their limitations. They were not originally designed to study the Heliosphere or the interstellar medium. Their instruments, while sophisticated, are not tailored to map the Heliosphere comprehensively. They provide a point of data, a snapshot from their particular location in the vast bubble, but cannot map the structure as a whole. Moreover, their trajectories, which have provided a wealth of data, primarily focus on the nose direction of the Heliosphere, the side facing the Sun's orbital motion through the galaxy. This has led to significant gaps in our knowledge, especially concerning the tail region of the Heliosphere, where the solar wind slows and becomes denser before mixing with the interstellar medium. The tail could hold crucial clues about the heliosphere's overall shape and how it interacts with the interstellar medium, including how galactic cosmic rays penetrate and influence the solar system. Future missions are being proposed to fill these gaps. These missions aim to deploy more advanced technological instruments specifically designed for heliospheric research. By adopting trajectories that take them to different parts of the heliosphere, including the poorly understood tail region, these missions could provide a three-dimensional map of this protective bubble. Future missions require innovations in spacecraft design, propulsion, and survival in the harsh environment of space. Advances in technology, such as solar sails or ion drives, could propel these craft faster and further than ever before. Moreover, the instrumentation on these probes would need to be highly sensitive yet robust enough to withstand the intense radiation and particle fluxes encountered in space. The primary goal of these missions would be to provide detailed measurements of the plasma and magnetic fields that dominate the interstellar medium. By understanding these elements, scientists can better predict the behavior of the heliosphere and its interaction with cosmic phenomena. Such knowledge is crucial for improving the accuracy of space weather forecasts, which can help protect Earth's satellites and power grids from solar storms. Additionally, these missions could offer unprecedented insights into the fundamental processes of our galaxy. For instance, studying the interaction between the heliosphere and the interstellar medium could reveal new details about the life cycle of stars and the dynamics of galactic evolution. This could also have implications for understanding how similar protective bubbles around other stars might affect the habitability of exoplanets, potentially guiding future searches for life beyond our solar system. By pushing the boundaries of human exploration and technology, these missions promise to expand our scientific horizons dramatically. They symbolize human curiosity and the relentless pursuit of knowledge, showing that even as we begin to explore other planets and asteroids, the exploration of our own solar system still holds many secrets waiting to be uncovered. Thank you for watching. If you enjoyed this journey into the mysteries of the heliosphere and the exciting future of space exploration, don't forget to like, subscribe, and click the bell for more amazing insights. Stay curious and keep exploring with us. Enjoy!